Hey, IB Physics kids, Mr. Tima back here with 5.4 sound waves. Okay, full disclaimer there are a lot of videos in this notes, so these notes might seem a little shockingly long when you open them up. And I actually have a Mythbusters video we're going to watch towards the end. That's in a whole separate thing. It's a long notes in a regular thing. This might take a full period of the class just to do these notes, but they're really worth it. And there's a lot of cool things in here. So you should be able to skip ahead on this if you need to, or come back to it if you need to. But to start out with, I love this thing called Cynamics, which is the study of how sound works and how it's classified.
The film you're about to see has no characters. If you spare a little of your imagination, it is a film to describe to you the effect of cymatic frequencies on matter. Everything owes its existence solely, completely to sound.
So it's pretty cool. That was all real. Nothing was made up, you know. So it's really cool. Hopefully, I think it's made like jacked up. So it's awesome. But we'll be learning about all that stuff when we get into electricity and things like that. Um, so the one part about the flames, though, the flames were called a Rubens tube. And this little video, we're not going to watch this whole one, but there's a good part about two-dimensional Rubens tube. So here we go.
Yeah, go for it. Whoa! Now, you may have seen a Rubens tube before. That's basically a pipe with a bunch of holes in it, and you pump in a flammable gas and light it on fire. So you basically create a row of Bunsen burners. What's really cool is to play some sounds into the tube, and you can actually set up standing waves. That is, there are patterns of the vibration of the air where there's a lot of vibration in some parts and not very much vibration in other parts. Now, that affects the flow rate of the gas inside that tube into the atmosphere, and so it affects the height of those flames. So basically, you can visualize the standing wave pattern. I'm currently in Denmark with a team of physics and chemistry demonstrators who have taken this experiment to the next level. They've actually created a two-dimensional Rubens tube, a whole plane of Bunsen burners, effectively. How many holes in this tube?
2,500.
2,500 in this pyro board.
Yeah.
So we're going to see 2,500 little flames.
Yeah.
So do you want to light it up?
Yes, I really want to light it up.
Why did you make this?
Because we really like the Rubens tube, but then we thought, when you put on more fire, then it always gets better. And let's just turn it down. And then we can just try to find a standing wave. So this is below the standing wave.
Cool.
Yeah, it's really difficult to see it. We need a volume and then
So there's your standing wave. All right. The top would be like the crest of a wave or the antinode. And where there's a lot of vibration, the gas isn't coming through. This would be like your trough or the bottom. Okay. And then there's the top. And then they talk about some stuff. And if you ever wanted to watch this, you can find it. But like, here's a different one. Here's a way to look at it. All right. There's the top, trough, crest, trough, crest. All right. But then they play a little music, which is kind of cool. I'll let you watch that for a second. And so people are using this at their actual shows and concerts now. They're not just, it's not just like flames shooting out of there. Okay, these flames actually serve a purpose and they are following along with the song and everything. So it is kind of like a crossover between science and music. So it's really actually kind of cool. So again, properties of wave, there must be vibrations. And again, where these vibrations, where there's a lot of vibrations, all right, that's a high density. There's actually a trough where there is not much density. That's where we get a crest, which is kind of counterintuitive. We tend to think that crests are the strongest, but they're actually not. Crests are actually the weakest. The troughs are the strongest. All right, and this has to do with these compressions. So again, this would be like a transverse wave. This is a longitudinal wave, but it's the same idea. You can see the density right here. So the most dense, those would be the troughs, and the crest would be the least dense part. Okay, pitch, amplitude, and velocity. This all has to do with what's called the Doppler effect. The idea of that sound is perceived, the frequency of sound is perceived as pitch. Those things with a higher pitch have a higher frequency. Things with a lower frequency have a lower pitch. Okay, amplitude is the height of the wave, and the velocity, we say that, and this is something you're going to have to know for some of your problems, that the speed of sound is 340 meters per second. Okay, and you may have heard about things that can break the sound barrier, like our jet planes and things like that. And hopefully, in your physical science, they went through that. I know I do. And if you want to, we can go into that in more detail. All right, but obviously, sound can reflect just like light, just like regular matter waves, just like water waves, everything. These are the same things. Just kind of to prove the point that it doesn't matter if we're talking about sound, light, or water, actual matter waves, everything follows the same thing. All right, so that wave goes in and reflects off an object. That's echolocation. Those are bats. Those are sonar, everything like that. Here's something I always leave on here, but have you ever noticed when it's cold, you can hear things a lot clearer. Like right now in the winter, you can go outside and step on the ground when there's snow and it sounds like glass is breaking. Like it's like all the way across there. Like I mean, it is unbelievable. Like someone trying to sneak up on you on the snow would be hard because it's like the crackle of their feet. In the summer, it's not like that. Well, it does have a little bit to do with what you're stepping on, but it really has to do with the temperature of air. In the warm, humid air, it's hard for sound to travel because it has to try to vibrate through all those particles in the air and it has to take a more arced direction, if you will. In colder air, it's more of a direct pulse because there isn't much in the air. So, not only a colder air, which leads to less humidity, and warmer air, which again has to do with that, has more humidity. So, it's not as able to transmit that sound. Okay. If you ever played outside sound travels so much faster, or not faster, but seems to be more clearer in cold air. Again, really quick, I always leave this on here for you guys, but as you get older, your ears are affected. Okay. As a kid, you can hear high frequency sounds. There's high frequency pitches that you can hear as a kid. Right now, it's 14 through 18 years old. That when you get to be my age, is 36 plus, you can't hear them anymore. Okay. And that's because that high pitch tends to travel. All right. But it doesn't travel as far as longitudinal, longer waves. Okay. So, like, for example, AM radio travels a lot farther than FM radio. Okay. FM is clearer than AM, but it doesn't travel as far. Again, a microphone, you may have heard about feedback and stuff. Well, if this stuff diffracts out, it's going to hit this microphone. If we start, reverberating as we move the microphone from top to bottom, all right, you can tell as we increase the intensity. Sorry, I should have drawn that. I don't know why I didn't. But right, we know the sound's going to come out here, and it's going to etch out. All right. Well, as the microphone moves down, it's going to get more intensity here, so it's going to sound louder. If the microphone's over here, it's not going to seem as loud. As the microphone gets down here, it's not going to seem as loud because remember, this is diffracting. I guess if I drew a little bit better picture there, that would help. But there you go. It's a little hard to draw with your finger on a computer. All right. Interference with sound, just like with the other stuff, obviously we can get those things to cancel out. This is what we call a soundproof room. Those cones, okay, as the sound comes out, they get trapped up in these cones. And instead of just hitting a wall and coming straight back, they hit into these cones and they kind of get trapped in there, and it kind of kills that sound, if you will. It reflects it inside and they get stuck in there. All right. So sound waves cancel, just like matter waves, okay? I'm trying to draw this as best I can. Okay, but we know that there is constructive waves and destructive waves happening, okay? So at A, we're going to have a constructive wave. At B, we're going to have a destructive wave. All right. So again, because they're going to cancel out on this side, and they are going to construct right here. All right. Again, high notes have a high frequency. Okay. So with a high frequency, that would be a high note. With a low note, we have a lower frequency. Loudness has nothing to do with frequency, though. Loudness has to do with amplitude. So even though this would be a high note and this would be a low note, they would be at the same volume. This would kind of be like a slow, mellow song. This might be an intense, fast pop song. But if they're at the same volume in your car, they're going to be at the same volume. The only way to increase the volume is to increase the amplitude. But realize if we increase the amplitude, the song doesn't speed up or slow down. These are still the same songs. They're just at different volumes. Okay, you kind of with me? This all has to do with the idea of standing waves in a closed pipe. Now, when we talked about a guitar earlier, those harmonics, that was an open, like a string instrument. These are closed pipes. Okay, so the note comes in and reflects back. So if you notice, the other one had a 1 harmonic, a 2 harmonic, and a 3 harmonic. These are only on the odd harmonics, and that's because of the idea of a closed end tube. I'm not going to really get into it that much. I don't want to get too much into this. They tend to not ask too much about these, but this is all about the idea of like instruments. Okay, all your instruments are played like this. All right, resonance. Okay, we've talked about resonance a little bit, but resonance is the idea of increasing the, shall we say, amplitude of that wave. So that's how we can break a glass. If you rub your finger on a glass, you're gonna find the fundamental frequency. If you increase just that frequency, the amplitude, not the difference in pitches and sounds, but that actual amplitude, it will begin to vibrate and those waves will kind of get out of control. You're going to watch these videos. It's kind of a broken up 5-segment Mythbusters video. You'll see that on Schoology or in your assignment folder, and you will be able to watch that, and that will be very huge. But what's kind of cool is, and we'll finish our notes here with this, is there's the Tacoma Narrows Bridge. So there was a guy that was in charge of building this bridge, and what he didn't think about was there was a natural breeze that flowed between this valley or this depression, okay? And this natural frequency of the air met the natural frequency of the bridge. And what happened was, because of resonance, because these waves kept constructing and constructing and constructing, and this little vibration turned more and more and more violent, okay, there was a catastrophic failure of the bridge. Okay, so we're going to look at that. This is actual footage from that time. I'm going to blow it up. It's a little hard. It's a little grainy. We're talking about in the 30s and 40s here. That was the dedication. Now look at this. There's a guy walking right here. They thought it was cool. It was like, hey, look at this bridge wobbling, man. Look at this bridge. Look at the lights. Okay, it keeps getting worse and worse and worse. People would come and try to run across it. People were still driving across it. They were selling tickets. They're like, come walk across the bridge. Yeah. Look at it. It's a little hard to see, but look at it moving right there. Okay. And then finally, right? I mean, look at that. Look at that. Could you imagine driving across that? I mean, look at that. I mean, that's probably a difference of 30 feet. You'd almost feel like your car's going to get launched off of there. So at this point, obviously, people would try to drive across and they'd get scared and they'd run out of there and everything like that. And eventually, what's going to happen, right? We all get it. The bridge is going to break apart. It literally can't do it. Needless to say, I mean, we don't think about that with bridges, but it's very, very important. All right, last little video here. Last little video for you is something that connects all of this to biology and into the future about where we're talking about. And that's right. What are waves and why are they important and how are we using them? Well, I think this is fundamentally unbelievable that this could be the difference in our future is sound waves.
So now we're searching for the magic frequency. And we start with 100 hertz and we look through the microscope to see if anything's happening. We watch for 5 minutes. Nothing happens. We try hundreds and hundreds of frequencies, if not thousands, until we find the magic combination. Because we believed there just had to be a better way. There had to be a better way. And we think we may have found it. I have here 2 identical tuning forks, both tuned to the note A, the note an orchestra tunes to. These forks are both made to vibrate 440 times per second. We say their frequency is 440 hertz. If I tap this fork, putting little pulses of energy into it, the second fork will also vibrate in sympathy. And if I silence this fork, we just may hear the other singing its tone. We say that I'm inducing a sympathetic resonant vibration in the second fork. It only works because both forks are tuned to the exact same frequency. Now, many of us have seen this very charming young man on the internet who shatters crystal glasses with his powerful voice. But if you watch him carefully, you'll see that first he taps the glass with his finger and listens. The glass sings its natural resonant pitch. Then he takes a deep breath and sings a loud, long note. He induces a resonant vibration in the crystal glass. The vibration grows larger and larger and larger until the glass is shattered. On the other end of the scale, we have a giant bridge made out of concrete and steel, a suspension bridge, the Tacoma Narrows Bridge. Cars and trucks and buses are going over it every day. And unfortunately, where they built this bridge, there was a steady wind blowing across it. And one day this wind induces a small vibration in the bridge, hardly noticeable. But the frequency of the vibration matches the resonant frequency of some part of the bridge. And the vibration gets larger and larger and larger until the bridge collapses into the river below. A destructive resonant frequency. So on one end of the scale, we have a giant concrete and steel bridge destroyed by resonance. And on the other, we have a small crystal glass shattered. So maybe we could shatter something even smaller, something really small, something you would need a microscope to see. Maybe we could shatter a living microorganism. So maybe we could change a biological living liquid crystal with a special electronic signal. But in order to do that, we would need some kind of device. So we search the US patent database, and we find this invention by a physician, Dr. James Bear of Albuquerque, New Mexico. It's called a resonant frequency therapy device, and its purpose is to induce a resonant vibration in a living organism or cell. If I put in, say, 100 hertz, out will come 100 pulses per second. If I put in 200 hertz, we'll get 200 pulses. So now we're searching for the magic frequency. And we start with 100 hertz, and we look through the microscope to see if anything's happening. We watch for 5 minutes. Nothing happens. So we try 101 hertz. We look through the scope for 5 minutes, and nothing happens. So we try 102, 103, and so on. Over the course of 15 months, we try hundreds and hundreds of frequencies, if not thousands, until we find the magic combination. The answer is you have to have 2 input frequencies, one low, one high, and the higher frequency must be 11 times the lower. It's what we musicians would call the 11th harmonic. When we add the 11th harmonic, we begin to shatter microorganisms like a crystal glass. These are the first videos taken. We showed these videos to our friends in the biology department. They said they hadn't seen anything quite like it. Seems to be a new phenomenon. These organisms are being shattered by our electronic signals. We now know that cancer is vulnerable between the frequencies of 100,000 hertz and 300,000 hertz. So now we attack leukemia cells. Leukemia cell number 1 tries to grow a copy of itself, but the new cell is shattered into dozens of fragments and scattered across the slide. Leukemia cell number 2 then hyperinflates and also dies. Leukemia cell number 3 then tries to make another cancer cell. The new cell is shattered and the original cell dies.
So it is crazy to think, and this man, Nikola Tesla, we're going to learn about very shortly, but it is crazy to think that the cure for maybe leukemia, maybe for cancers just in general, may exist by just you walking into a chamber where we have a bunch of speakers hooked up and we let you sit in there for 20, 30 minutes for a session and hit you with frequencies, different frequencies, and it literally would shatter just those bad cells and keep everything else the same. Amazing to think about, amazing to think that when science can share and cross over, what they can come up with. Again, apologize for the length of the video, but there was some cool stuff in there. We'll talk about it in class, and until next time, Mr. Team is out.